Hi everyone, thanks for being here. Today we're going to explore the power of eBPF for system observability. I'm Shay. I'm a site reliability engineer at tonies.
Hi everyone, I'm Zahra Dehghanpour. I'm a platform engineer at Boy.
So, let's start with a story. Imagine it's 2014 and you're the application developer on the left. For finding the root cause of a latency problem in your product, you need a new piece of information from the kernel to observe it properly. So you go to the kernel developer and say, hey, can you please add this feature? And the kernel community, rightly so, is extremely careful about what they add. The response is okay, but we need to make sure this is good for everyone, and that it is perfectly stable. A year later, if you're lucky, the feature gets merged into the upstream kernel, but that's not the kernel your servers are running. You have to wait for the specific Linux distribution to adopt a new kernel, and years later, the feature finally arrives, but at that point, the world has moved on and your requirements have changed, so this wouldn't make sense so much. And this cycle was the reality. It was slow, frustrating, and it made deep system observability a luxury that not anyone could afford. So I'm just curious here, has anyone here ever tried to add an observability feature to the kernel only to back away because it was too complicated? Okay, maybe you guys didn't even think about it because it's a painful process to even think about adding something to the kernel just because of something observability. And this painful process is the problem that eBPF was designed to solve. It breaks this cycle by asking a revolutionary question. What if we could get the information we need from the kernel without having to change it? So has anyone ever heard about eBPF? Well, that's nice, quite a lot. eBPF is a revolutionary technology that allows you to run a sandbox program within the Linux kernel itself. It's like a mini computer or a virtual machine inside of the kernel. This is a game changer because it actually allows the developers to safely and efficiently extend the kernel's capabilities without having to recompile it or load some new kernel modules. What does it stand for? It is the Extended Berkeley Packet Filter. Now the BPF technology has been around since, I think, 1992. And to put that in perspective, this is something that's been here and that's been older than maybe a good chunk of the people in this room. Originally, it was designed for one specific job, filtering network packets, which is like the tools like TCP dump actually use that still today. And the E in the eBPF is what makes it interesting. It stands for extended, which means that it turns it into a superpower for the entire operating system that goes beyond just networking into observability and security. And this brings us to the new reality with eBPF. Let's look at the same scenario again. This is the application developer, has the same exact issue, and says that I want to add a new feature to observe my app. But now, instead of going to a kernel developer, he goes to an eBPF developer or a site reliability engineer and asks for this feature. And they say, OK, give me a few days, not years. And after a couple of days later, the eBPF developer comes back with a solution, like an eBPF program that safely hooks into the kernel to extract exactly what it needs without even, when you want to run it, without even needing you to reboot your machine. And because it's not a kernel module, it's a safe sandbox program that can be loaded and unloaded on the fly without any risk on your system. And this is the power of eBPF to transform observability from a slow and dangerous multi-year process to a fast, safe, and agile one. So how does eBPF actually pull this off? How can it be both powerful and safe enough so that it would not cause kernel panics or something? And the answer lies in this fundamental architecture. To understand its magic, we have to first talk about the words in the computers. We have a user space and a kernel space. The user space is the world where all of our application lives, like the web browser, your code, and everything. It all runs there, and it's protected and restricted. An application can't just decide to access the network card directly or access a file block, because it would be chaos. And then we have the kernel space. It's like the heart of the operating system. And the kernel is the ultimate manager that controls the hardware, the memory, and scheduling the processes and everything. And it has the ultimate power and privilege. And these two words are separated by a sacred boundary. And for an application in the user space to contact something in the kernel space, it has to ask kernel for the help. And this formal request is called the system call. So how does eBPF breaks this sacred bond safely? It actually uses an event-driven architecture. It's all start with an event. This is anything that happens in the kernel that we want to observe. This could be a system call being made, a network packet arriving, or a specific kernel function being executed, which we choose which event we want to hook into. And then our eBPF program runs. We write like a small sandbox program will be attached to the event, and when our chosen event occurs, the kernel immediately executes our code. And then the program injects the data back to user space. So we talked about like going into the kernel and doing some risky stuff. How many of you thought if this is actually safe? I see quite a few. So for it to actually prevent from anything bad to happen or crashing the entire system, we have this crucial component in the eBPF architecture, the verifier. Let's walk through the flow of the eBPF program. Everything starts at the user space. There is the code, probably in C, Rust, or some low-level language, high-level language. And then the source code is compiled into the eBPF bytecodes. And the applications uses a BPF system call to ask the kernel to load this bytecode. But before the kernel accepts this code, it hands it over to the verifier, which acts like a strict safety inspector. And it performs like an analysis to see if there would be any crashes of this program, are there any infinite loops, or does this program even have privilege to do this? And only after the program has passed all of these, it can be allowed to be attached to the kernel. So.
OK. Let's take a look at a very basic Hello World example to understand how eBPF actually works. Here we have a very basic program which actually tries to print some Hello World. As you can see, we import the BPF from BCC library. BCC library is a library for Python, which allows us to write our eBPF program, and then it compiles it to eBPF bytecode. So it makes our job easier. Then we define the eBPF function that we have. This is simple. We are using a eBPF helper function here called bpftrace printk, and then print the hello world. In the next line, then we are trying to actually load the function that we wrote to BPF. Actually, it compiles it to eBPF bytecode and then send it to kernel. The next thing we need to do is actually hook it to some events. Here, we are trying to hook the function that we wrote to clone system call. Clone system call is a system call that creates child processes. So we hook this function to clone system call. Whenever this system call gets triggered, our function will run. And then we are trying to print the result. OK, here, as you all know, demos are not usually on our side, so we try to actually record this beforehand, so we can just discuss it together here. Here is the file that we discussed already. We are trying to run this and see what happens. And for sure, since it's a Python file, we are running it with Python. And then let's try to run a simple command like a ls. As we can see, the ls command triggers the clone syscall. So as a result, we have a hello world printed in the console that we have. And we also have some background process which triggers clone, and therefore we are seeing this. OK. The helper function that we have seen, the bpftrace printk, is actually great, but not for the real-world scenarios. If we want to have some real-world observabilities, then we need to find actually a structured way to send the data from kernel to user space. This is where eBPF maps come to the picture. An eBPF map is actually a highly efficient data structure that lives inside the kernel, but it actually acts as a bridge between these two worlds. Let's take a look at the picture that we have here. We have some eBPF programs. They are triggered by some events. They can actually send metrics, store some data to the eBPF map that we have. And this is the key to efficiency. Instead of sending a message for every single event, we can try to aggregate the data all in the kernel. And also in the other world, in the user space world that we have some application that can actually gather metrics from this map, and they can pull the summarized data, not a raw firehouse event. This map-based communication is actually what makes eBPF so powerful, so we can build some sophisticated and high-performance observability tools. OK, let's take one step further. Let's see how we can use eBPF for actual tracing and monitoring. As we see, we can attach programs to different points in kernel or application. As an example, in the kernel, we have something called kprobe. A kprobe is actually a Linux kernel mechanism that lets us dynamically attach to almost any kernel function that we have and then collect information when that function is called. This gives us a powerful way to look inside the system and actually see what's happening. We have some tools like BCC, bpftrace, and Hubble, which are built on top of eBPF to make tracing and monitoring much easier. We have some example. We got all of them from the BCC, and we are trying to demonstrate each of them. The first example here is exit snoop. We want to observe all the processes that we have. For sure, we can run, for example, htop command to see all running processes. But what if we want to also observe the short-lived processes? This is where this example comes in handy. We can see all the short-lived processes with their exit code. OK, don't worry, we don't want to go through all the lines here, but we want to explain the logic behind the code. As we can see here, we are using eBPF map here. Those lines that start with a struct, they are defining some map. And we are trying to get the information of all the processes with their process ID and with their exit code. Let's try to run this. First, we run the code that we have seen together in the previous slide. As we can see, there is an IP table process which was running and exited with the exit code 0, and it's running quite frequently in the background. Let's try to run another one. For example, a simple ls command. We can see that here with the exit code. And let's try to run some dummy command which actually doesn't exist to see what happens. As we can see that command not found with the exit code 35112. And we can extend this to all the processes that we might have in our servers. The next example is out of memory killed, or OM killed. I'm sure everyone here has run into an OM kill at some point. Let's see how we can use eBPF for these kind of events. As we discussed before, we have something called kprobe, and actually we can use it to attach to any kernel function that we have. There's a kernel function called omKillProcess. This function is responsible for killing a process when system runs out of memory. We can write a kprobe handler like this, then attach this to the omKillProcess, a kernel function. Whenever this function calls in kernel, then our kprobe handler will run afterwards. What we can do here, we can try to get some data for sure. First of all, we can see which process triggered OM kill. Next, we can see which process got killed because of OM kill, and then some general information about the memory pressure at that time or the average load of system at that time. Here we are running the code here, and let's try to produce this case, try to run something that consumes memory quite heavily. For example, a perl command in a while true loop. See what happens. Then we can see that it got killed because of OM frequently. There's something interesting here. We can see another process called containerd with a process ID 821 is actually got killed because of the perl command that we ran. And also we can see the load average at that time. So it's quite nice.
So turning kernel into an open book for observability is a game changer. But that's not the only part of our eBPF story today. The same technology that let us see what's happening inside of the kernel gives us also the power to control. And this can be really helpful, especially when it comes to networking. eBPF enhances networking by enabling efficient packet processing. This enhances the network performance and flexibility and making it more cloud native ready. And some projects that use eBPF for networking include Cilium or Tetragon, for example. A prime example in networking is how Cilium revolutionized Kubernetes. Traditionally, Kubernetes uses a tool called IP tables, which is like a very long checklist, and every single packet that comes in, it has to go through all those chains to see where should this packet go, if this is allowed or not. And actually, as the cluster grows, it makes everything so slow. But Cilium throws away and uses an eBPF map, like a super fast hash map or like an address book. So when a packet arrives, an eBPF program does a single direct lookup and find a destination instantly. And the result is we have a more scalable and fast network. no matter how big our cluster gets. And this is like a perfect example of replacing like an old slow mechanism with an eBPF native one. But what if we need to handle millions of packets per second, like a DDoS attack that's coming and we have to act fast, or high-performance load balancing? For that, we need to move to the absolute front line of the network stack. And this is where XDP, Express Data Path, comes in. Let's get into the specific of how XDP achieves this incredible speed. Its magic is its location. And it gives us a hook point right into the network device. And these hooks run before the OS do any expensive work or like allocate a lot of memory in the socket buffer for the packet. And when the packet is received, an eBPF program is executed and it can perform several actions. It can drop the packet, let it pass, or redirect it. This might sound a little complex, but maybe we can dive into an example so that we can actually see how is it happening. We can write and load an XDP program that can act as a smart firewall. To make it more simple, here its only job is to drop every ICMP packet from a specific interface and let everything else through. This is the C code for the XDP firewall. It can look a little bit intimidating, but the logic is actually really simple. It gets the packet and check if it's an IP packet or not. If not, just let it pass. If it's an IP packet, then it looks at the IP header. Is this an ICMP packet or not? And then if it's that ICMP packet from that specific interface, then it will return the XDP drop and actually drop the packet. And in other cases, it will use the XDP pass and pass the packet into the kernel networking stack. So in just like a few lines of code, we can build like a smart and high-performance firewall that would remove the exact traffic we want to block before it reaches to the Linux network stack. And here is like a test run for it. We want to ping the local host, as you can see. Everything is smooth, and we can see the packets arriving and sending the reply with TCP dump here on the localhost interface. And then we are going to run our program. It attaches that to the interface. And then as it is running, you can see that we cannot ping the local host anymore, and there are no packets going. So it's like that the packet is being seen and dropped before it's even can be captured by tools like TCP dump.
OK, let's go from the visibility to control with eBPF. So far, we have seen eBPF can be used for performance and networking. Now let's talk about one of the powerful use cases that it also has, security. eBPF can work with Linux security module to watch and control security events while system is running. And it lets us see both system calls and network activity, which gives security tools much more context and control than the older method that we had. Examples of such tools are Falco and Tetragon. Let's talk about the Tetragon. Tetragon is actually a modern security tool that provides deep observability and real-time enforcement in Kubernetes. And because it's powered by eBPF, it can see everything that is happening at the kernel level. This includes every single process is executed, every sensitive file that is accessed, and every network connection that is made. It can see these events in real time with very, very low overhead. Let's see it in practice. There is a custom resource definition in Kubernetes called tracing policy. Here we are using it for file monitoring. We can also use it for the network, but for this presentation, we are only focusing on file monitoring. As we can see in the last line that we are seeing, we said that if someone tries to read the etc shadow file, which is considered as a sensitive file, then try to get some alert or some event to observe it later. And we installed Tetragon as a daemon set for all the nodes in Kubernetes. So we have a cluster of 3 nodes. We have Tetragon pods on each of them, as we can see. And then we have a test pod here, the last one here. And we are seeing that it's running on the worker 2. And let's find the Tetragon pod that is running on worker 2 also, because they are running on the same node, so they are sharing the same kernel, so it can understand and observe everything. Let's exec to the Tetragon pod that we have. We can use the CLI called Tetra to actually get events for a specific pod that we want to have. Here we are saying that the pod that we are interested in is actually the test pod that we have called Zwing. And let's actually try to exec to the test pod and try to read the content of the file etc shadow to see what happens. As we can see, there are some events here, and there is a full log consisting of the timestamp, the pod, everything. We can also see. And here it's used for observation. We can also use it in the enforcement mode. So no one, for example, can read the content of this file.
So let's bring it all together. We started our journey with a look at the past, a time where kernel was like a black box, trying to understand it was a really dangerous process. We saw how eBPF completely changed this reality, and thanks to the safety guarantees, it turns the kernel from this black box into a fully programmable and observable platform. Today, we've only scratched the surface. We gained some deep observability with BCC tools. We unlocked some networking performance with XDP and saw some security measures being handled by Tetragon. And the most exciting part is that this is no longer a niche technology, and the eBPF ecosystem is growing and powering a lot of critical software in the cloud today. And I highly encourage you to go home and install these tools and start exploring. And because the power of safely and deeply understanding your system is now in your hands. Thank you for listening. We have some time if you have any questions. Yes. So the question was that if we can compile the kernel ourselves and do everything we want, then what does eBPF brings to us? The thing is that that's a complex process. For a lot of people, it would be something that they never want to touch. They're scared of messing something up, and it would be a little bit harder to understand. But with eBPF, it would make it more accessible, make it more understandable for everyone who's trying to understand the kernel and try to start programming or getting metrics and observability features from there. So I think that's a cool part of it.
And maybe also, let's say that if you want to run the kernel that you are compiling yourself in your production servers, then you need to also, for example, upgrade it, patch it for any CVEs, and you don't know, for example, if the eBPF code that is running today, it's going to run tomorrow with the new changes that you are pulling from the upstream. So I think there is no other question.
Thank you so much, and have a nice day.